Jérôme Pratlong, Chief Engineer at Teledyne E2V for Space Detectors. I'm going to talk about hyperspectral detectors, and I will start by a brief reminder. Hyperspectral missions are very important because hyperspectral system can output a spectrum from the object under analysis. And as each material has its own light spectrum signature, it provides a very important number of information about the object looked at. This is a big step from the previous type of technology, such as multispectral applications. Effectively, in the case of a multispectral application, the intensity of a light reflected from the object is outputted per discrete wavelength, providing a intensity versus wavelength spectrum that is in a way digitalized. Therefore, the gap between two wavelengths will have to be modeled. In the case of an hyperspectral, that's different, as the system will output a range of wavelength from usually 400 nanometer to 2.5 micron, representing the radiation spectrum of the sun, that in a very small step of 1 nanometer, provided a very precise spectrum of the object looked at and analyzed. This gives way more information, and with today the power computing that we have, that enable in a reasonable time and cost to extract more information in one image. We can see that the hyperspectral output is what is also called an hypercube, where you got 3 dimensions. In the Y and X axis, you've got the 2D image, and in the third dimension is the wavelength and the spectrum. Hyperspectral covers a large range of applications: environmental, urban planning, climate science, oceanography, security, helping to monitor climate change, forestry management, disaster, but also pollution, atmospheric analysis, water quality, or again, chemical and biological threat, for instance. In terms of system, there are today 3 ways to do hyperspectral and 3 ways then to build an hypercube. The first one is a line scan based technique where the object or the area is scanned and generates one by one the different columns, creating the hypercube. The other technique is a wavelength scan based on a color filter wheel that will output each wavelength at a time, building the hypercube by outputting row by row. The last approach is called a snapshot scan, where in one image, the hypercube is generated. Typically, a 2D array detector is used. There is not as such a standard format for hyperspectral. However, there are typical formats. The pixel pitch tend to be around 20 to 30 micron. This is quite a large pixel pitch, and this is to handle large fuel capacity that this sort of mission need. The number of rows are typically around 512 rows, up to 1 kilo rows. The number of columns varies following the swath, but in general, not below 2.5 kilocoulomb. For very large detector, some options are to stagger smaller detector into a focal plane. Pixels are designed with 2 to 3 gains in order to adapt each band or each row to the intensity or the wavelength projected onto the detector, as the intensity can vary a lot per wavelength. The implementation can come in 2 ways. One is a dedicated design, which mainly means around a large pixel, 25 to 30 micron. The advantages are that there will be no need to further processing like binning afterwards. The macropixel is the same size as the pixel. It tends to have a larger full wave capacity, but a lower signal-noise ratio. It can potentially be higher frame rate, and definitely it will have the lowest data throughput. From a cost perspective, it's also interesting to investigate the generic purpose approach, where a generic purpose detector is used, usually with a smaller pixel pitch, 10 or 15 micron. That will require an external binning in order to create the macropixel of 25, 30 micron. Tends to have a lower full wave capacity, but a higher signal-noise ratio. The frame rate tends to be lower because there are way more pixels to output. And as a consequence, also, it will have a higher data throughput that require more memory at the front-end electronic. One important performance that is really critical for hyperspectral is the sensitivity of a detector to the light, and in the near infrared, how much fringing there is. The fringing is a form of oscillation, as we can see on this graph, that is coming from the fact that the light coming into the detector, and we can see that in the bottom drawings, from the back surface of the detector, in this case, and can reach the front side of the detector, from which the light is reflected, bouncing back to the back, and part of it transmitted back outside, creating an interference with the incoming light. At Teledyne E2V, we developed a specific process that we call graded AR coating in order to remove this phenomenon, that by having a coating that goes from UV to AR infrared, but at the same time by adjusting the thickness of this AR coating in order to prevent this reflection at the front surface of a detector. It's really important to remove this fringing effect, since, as we can see, it's quite high frequency, and therefore, what does that mean for the application? Is that technically we cannot know what will be the QE for a given frequency in the near infrared. This is an example from Truth mission, where we use a single detector, sensitive in the visible and in the infrared. This is based on MCT material with substrate removed. The name of this detector is ChromaD, is a 2K by 1K, and it is used in the Truth mission. Truth mission has 2 objectives. One is to create a standard laboratory in space for climate measurements, for global warming and humanity impact monitoring, and serve as a reference for calibration for other Earth observation satellites, and therefore will enable metadata from other missions. And will also cover the large growing market for commercial applications. This detector is sensitive from UV to SWIR, 320 nanometer to about 2.5 micron, with a resolution per row of 2 nanometer, and has two gains, one 1.1 mega electron and the second one 400 mega electron. As you can see on the QE curve, the sensitivity of the detector is quite good from UV to SWIR, with about around 70 to 80% across the whole wavelength. Thank you.